Hi, everyone. It's my pleasure to introduce Dr. Iacopo Masi, and he's an associate professor in the CS department at Spagna, University of Rome. He is also the principal investigator and founder of the OWN lab. He was an research assistant professor and research computer scientist at USCSI. He has served as an area chair for several CV conferences and is an associate editor for the Visual Computer International Journal of Computer Graphics. With that, the stage is yours, and thank you for your time.
Right. Okay, cool. So thank you for the warm introduction. And my name is Iacopo Masi. I am a professor from the computer science department in Sapienza, University of Rome, and where I am running the Omni lab. So it's actually a pleasure to be here at ISI today. And today I'll be talking about robustness and generative modeling. Okay, so it's actually interesting that my current research, it was seeded from when I started at USC ISI. So here you can see a picture that I took from my office downstairs. And today we'll be talking about on things that are related to the DARPA Guard project, which is the last project that I was working at ISI. So as I said, in Rome, we are the Omni lab, where we do research about machine learning and deep learning applied to the visual domain, but also now we are working on NLP and computer graphics. And currently I have 4 students, Hussein, Antonio, Adrian in co-supervision with Professor Rodola, and then Maria Rosaria in co-supervision with Professor Lisanti. And before them, I had Sena that moved to the industry, and I co-supervised MODSDE with Professor J. Kuo at USC. Okay, cool. So in this talk, we'll be mostly, I will. The work, it will be powered by the work by Hussein, Maria Rosaria, Senad, and MODSDE. And I thank my sponsorship of the grant, which are the Future Artificial Intelligence Research Fair, and also the Project PRIN, funded by the Ministry of University and Research in Italy. Okay, cool. So let's head towards the talk outline. My talk is divided into 4 parts. In the first part, we'll try to answer the question of why robust classifiers, they behave as generative. So this is an introductory part. And then in the second part, we'll try to make a connection between adversarial attacks and energy-based model that is hidden inside classifiers. And then third, this is the most interesting part of the talk, the core part of the talk, where we do a lot of analysis. So we'll shed some light on robust classifiers under the lens of energy-based model. And finally, a few applications. I will show you how we can do image synthesis and image editing with robust classifiers. Okay, so let's move ahead and try to answer this question. Why robust classifier behave as generative? So we'll take a step back and try to define what is generative AI. Now, we all know that generative AI, it's on the rise. And there are probably multiple definitions that you can give, but a way that I like to think of it is it's a way to map random noise to actual structured data. Okay, so and once you do this kind of mapping, you can think as a trajectory that you're walking from random noise to structured data. So what do I mean by that? If you consider the image domain, you can think about the space of all possible images. Probably out there, there are a lot of images that don't make sense, and there is a tiny portion of the space that is occupied by the natural images, which are images that you may find by taking picture in the world, and we may have, for example, cats and flowers and bird and so on. So how you can think about generative AI. Generative AI is that you start from a random point and somehow you follow some kind of signal that it's guiding you and landing you towards where the data it's meaningful. And I believe this interpretation it's even nowadays more appropriate given the rise of diffusion models and the noise in score matching model. Okay, so actually we can see this in an animation that we did for one of our paper, Magic. So we are start from random noise and we inject some sort of notion of the shape of the object, and we try to here translate the hummingbird until we arrive to something that it's meaningful. Okay, let's say generative AI it's a higher level, but at the end when we talk about generative AI, what we mean is generative modeling. So how you can define generative modeling? Generative modeling, basically, we start with a sparse set of training points. If you consider the image domain, you can think these images as a point in high dimensional space. And okay, now you have the points and you assume that they are generated from data generating distribution that we don't know. And then what do? We try to learn a parametric model that it will hopefully approximate the data generating distribution. Now, with generative models, unlike discriminative models, there are multiple things that we can do. One of these, it would be to sample from the model. So now you can sample from it and you have X prime. And if everything went well, you check X prime, you check Xi, and you say, oh, I generated something that, like it's not the same as the training point and it's similar, it makes sense. So in the past, we have had a lot of generative models, for example, Gaussian mixture models. And then in the deep learning era, we had approaches that try to reconstruct the input, such as VAE. And in the last decade, we had generative adversarial network, GAN, and now we have a full wide of range, such as autoregressive models. We know all them from LLMs, and normalizing flows, energy-based model, and diffusion or denoising score matching model, which are basically the same. Okay, cool. Despite in this talk, we have all this variety of models, we are actually trying to do generative modeling in a different way, which is by inverting a discriminative and robust classifier. Okay, so what do we mean with the robust classifier? So if you have a classifier, usually you receive some data X and you want to predict Z, which like it allows you to solve one task that you have at hand. For example, if you want to perform face recognition, image recognition. So here you see, if you have a classifier, you are not really modeling the density of the data. So X is given, and then you want to predict the Z, right, in order to solve your task. So we can visualize this with this plot, where here you have all the input point, and maybe this is your training point, and what do? You try to work in the, let's say, forward mapping. So you want to map X to a latent code Z, and you want to build this latent code so that it's solving the task that you are performing. For example, like face recognition or other things. And once you build Z, you want to build Z in order, like that you lower your loss. Okay, that's cool. So the forward mapping. So what do we mean when we build a robust classifier? Now you fix Z. So now Z is fixed, and you actually try to invert the mapping and go back in the input space. And if you do so, then you have a full set of points that they may map to Z. Okay, so here, once you are in this condition, you can take different paths. If you take the path of adversarial attacks, then you say, okay, let's define a metric in my input space. So now, like I want to stay close to Z into an epsilon ball. And then you get a perturbation that it's not in that set. And actually, in this perturbation, it will cause large deformation of the latent space. So maybe now you have another Z that it's actually hugely increasing the loss. Okay, so with this in mind, if you look at the picture, you say, oh, no, doesn't work well because for bounded variation of the input, I want bounded variation of the output, right? You want the system to be smooth. So what do you do after that you crafted the perturbation with max? You say, okay, now please change the weights of my model, of my deep net in this case, to restore the right connection, right? So to lower the loss on adversarial data. And this is what we call standard adversarial training. You play a min-max game where the max, you first generate sample to increase the loss. And usually you do so by actually doing a lot of iterations. And then you change the weights to minimize the loss, okay? Okay, if you do so, and we will be using SAT in the in my talk to indicate this process, some kind of strange and mysterious things happen. The model becomes robust, but it becomes also more aware of the data density, right? It becomes more aware of the data density, and the accuracy on the natural data decreases, and also the model develops these generative behaviors. So what do we mean with the generative behavior? If we look at the input gradient, so what are we looking at? We are looking at the gradient of the cross entropy loss with respect to the input x. We'll notice the following differences. So for example, if you have, let's say, a standard ConvNet trained on ImageNet and it's standard non-robust, we look at the gradient and we interpret it as a saliency map. You can see here that the attention of the saliency is on actually, I would say, maybe the texture of the animal. And if instead you use the same, you do the same, but with a robust model where the data, once it was trained, it was deformed a little bit into this epsilon ball. You see that the saliency now it's into another place. And if you increase the epsilon ball in the training, and then you do the same kind of inference of the gradient, then you see that the saliency is on parts, in this case of the animal, that they are more, in literature, they say align with the human perception, right? So we are talking about gradient that they are more aligned with the human perception, because simply you look at them, you say, oh, maybe here it's focusing on the eyes, the mouth of the animal, and so on. Okay, cool. So now let's try to slowly answer the question why robust model behave as generative. So there is this very nice paper from ICLR 2020 that it's teaching us how we can take a classifier and reinterpret it as a generative model in the special form of an energy-based model. So in a nutshell, what is an energy-based model? You want to model the density of the data. This is a very hard problem. So what do? You try an approximation of this, and you say, okay, I will not model the partition function, because with deep net and the input space, it's very large. So I will not do this, and I will just model the energy, which is a vector to scalar function that you can think it as a sort of inverse of the probability. So if the energy is high, then the point it's less likely to exist. And if the energy is low, then it means that it's highly probable. One drawback of the energy is that it doesn't give you a reference point calibrated, like probabilities they go between 0 and 1. The energy can be -50, and you don't know where is the reference. Okay, so cool. So this paper, it's telling us that we can take the softmax classifier and reinterpret it with as an EBM in the following way, very simple. So you have the joint energy of X and the label that you have, which is simply minus the logit. This is super simple. And then something that is hidden inside is this marginal energy. So what is this? This is a sort of, the model, it has notion of how much the data it's likely from its own view, right? So this is something that usually we discard, we don't consider. And with this tool, we can actually rewrite the cross entropy loss in a different way. Instead of doing minus log of the softmax, we can rewrite it like this, okay? So the cross entropy loss, now, if you rewrite it like this, you see that it's bounded at the minimum at 0. So this happens when the left energy is equal to this part, and it cannot go less than 0. Okay, so actually here, with this in mind, I am proposing a new view on the way we train deep nets. So by the way, this plot that I will show you it can work for example, CompNet trained on ImageNet, or like visual transformers, or even if you are doing NLP. At the end of the at the end of each time step, you have a classifier over like your vocabulary. So it's also working there in all this field. You have to have a softmax layer at the end, right, in order for this to work, and of course the cross entropy. So usually, once you train all this model that I mentioned, you look at the loss with a plot that goes like the one. So you have the loss in function of the time, and maybe like if everything went well, goes down, and then you may check the validation accuracy. And so on. So here, this is the new view that I am proposing. Okay, I'll try to explain it. So it's a scatter plot. On the x-axis, we have the marginal energy. Okay, and on the y-axis we have the joint energy. And you may guess what do we have in the diagonal. So in the diagonal we have all points that they are at loss zero, all points that they are at loss zero. So the model, it's done from a classification point of view, okay, in the diagonal. And then we said the loss is bounded to be zero at the minimum, so the plot cannot take value in this part, in the lower triangular part, okay? Okay, cool. So with this in mind, let's see on a, let's say, toy demo how this goes, the training. So this is on MNIST. The points are colored. If you see, those up there are the epochs that are going through. We can see and make notes on a few properties. So for example, the points that are here up there, these are yet incurring a loss and they are not classified well. And the model decides to give them a high energy. And then through the training progression, we see that there are all these points that are on the diagonal. And this point, they are already at loss zero, but the model secretly, it's still pushing the energy towards the left, right? So pushing the energy towards the left. And if you look at the other plot, you cannot see it, okay? So my conjecture is that you are not only classifying the data, but at the same time, you are also fitting, let's say, the point cloud of the data, right? So the approach is doing both fitting the data and also performing the classification. So this is a way, at least, to see that. Okay, so now we can better answer this. Why, if you have a robust model, it will behave as generative. On the left part, you have a plot of the energy with respect to, let's say, the input space. The input, it's high dimensional here to plot it with just with one line. Once you train, what do? You have the training point and you want to lower the energy on this point, okay? So here, this is standard training. And then if you go for robustness, you say, okay, let me perturb a little bit the point around X. So now you have X plus delta, and you do this optimization so that now actually the energy will be higher on this point, okay? And then if you do adversarial training, you say, okay, no, you have to lower the loss there. So it means that you lower the energy, and now around this data point, the energy it's more smooth. By the way, the take from this slide are from this paper, which is not from my group, ICCV21. It's a very good paper that says, look here, what happens once you do it for an energy-based model. So if you are training a generative model for an energy-based model, you do this. Now you have X, and you still want to lower the energy on X, because this is the data that we have seen from the kind of generating distribution. And then what do? Now you have another process where you ask from the model to generate new samples. So now you have X prime. And once you do that, you generate this point to lower the energy. So now, on the right part, you are in a condition that it's not appropriate, because you have the real sample are more likely than the synthetic sample. So what you do, similar to adversarial training, you change the weights to restore the right connection, right? That the synthetic sample, they are less likely than the real sample. And this is called contrastive divergence. Okay, so with this in mind, you can see that there is a connection between like the generative model training and adversarial training. So hopefully now we have a better understanding why they become generative. And with this mental model, with my student Senad in 2022, we started to look at the connection of adversarial attack and the hidden EBM that it's inside classifier. So that's what we found. We started to correlate this marginal energy with respect to the attack strength. And here, when I'm talking about attack, I mean untargeted attacks that are performed through PGD. So PGD, it's actually it's an optimization process, but it refers to attack. So it's projected gradient descent. And PGD, it has one parameter that are the iteration. So you can iterate the attack multiple times. So the first finding that we have found is that the untargeted attacks with PGD, it's decreasing the energy inside the model. And we also have found, obviously, that it's actually, so it's okay. So the untargeted attack decreased the marginal energy inside the model, and we have found that it's increasing the joint energy. So this was known because we know that we are fooling the classifier. So like you want the probability of the ground truth class to go low, which means you increase the joint energy. And then this was known, but I think what it was less known is that this new point that you are creating by doing the attack, from the point of view of the model, they are even more likely to exist than the natural data. And we believe that this was less known. At this point, one can say, "Oh, but we knew adversarial attack. You get very, if you look at the probabilities, you get very, very high confidence probability. So this is the reason." But it's not like this, because if you look at the energy, it's even more clear which is an attack and which point is clean. So the light blue one is the histogram of the energy of the clean data. And the red one is the histogram of the energy of adversarial data with PGD20. And you can see that there is a clear separation. So in the model, there is a hidden secret that it's telling you which data it's an attack and which data it's clean. And then also what we have found that this marginal energy decreases as the attack strength increases. So when we talk about attack strength, as I said before, we mean iteration in PGD, right? So you can do multiple iteration, and this is the animation that shows that. So you start with 1, 2, 3, 4, 5, and then if you arrive to 20, the energy of the attack, it goes drastically on the left. And you can also see that from the same plot where we relate the average energy with the steps in PGD. And as soon as you do 2 steps, the accuracy goes to 0 and the energy drastically goes down, right? So here, these numbers is the robust accuracy at each iterations. Okay, this allowed us to actually develop now an efficient and effective detector. Why it's efficient? Because the more the attack is strong, and the data, it's already, the model is already telling you how to detect it. You just have to swipe a threshold and the distribution are well separated. So you can build an efficient detector because you don't have to train anything, and it's effective. We, for example, are getting on ImageNet detection rate of 98% for about 1.3 false positive rate, and the same on CFAR10, the same detection rate at 1.6 false positive rate. And as a note, we know that this detector may suffer from targeted attacks and from auto attack, which is a very recent attack, and hopefully in the next part of the talk we'll explain why. So then with Senad we said, is there a way to bypass the detector still using PGD? And the answer is yes. So what do we have to do? We have to still fool the classifier and yet keep the energy of the adversarial data overlapped with the natural data. So we call this high energy PGD. So you change the optimization, you find new points that are increasing the loss and also pushing the energy on the right. And this optimization is feasible on a model that is non-robust and standard. So now you have the energy, they overlap. And now this is the trend compared to what we had before. You still are able to push down the robust accuracy to 0, but now here you have some sort of constant energy value across all the steps. Okay, so now we are adding the central part of the talk. where we try to shed more light on robust classifier under the lens of energy-based model. And this is a joint work with Hussein, Maria Rosaria, and still Senad. So the idea here is that we wanted to extend what we did before, but improving the analysis on more attacks. So we are trying to reconnect the attacks with the energy on multiple attacks. If you see here, I have two rows. Above, I'm showing the marginal energy, and below the joint energy. So we already know that PGD is pushing the marginal energy way to the left. And then here you see that the logit energy goes to the right, which means we are drastically fooling the classifier, right? So on below, once you see the red goes on the right, it means that we are fooling the classifier. And we also look at what you get with trades. So trades, we'll introduce it later. It's not properly an attack. It's not properly an attack. It's a way to train this model. But if you see trades, you get still this behavior as PGD, but now the logit, they have, let's say in this case, two modes where actually this part is fooled, and on the left, these are actually points that probably they were classified correctly before, and the attack is actually improving the confidence of the classification. Then we also look with the same plot at the Carlini-Wagner attack. So you see that below Carlini-Wagner, it's like doing a good job in fooling the model, so it's pushing the energy of the logit on the left. But if you look at the marginal energy, you see that it's doing this in a very subtle way, because the marginal energy is kept overlapped with those of the natural data. So actually, with this plot, we have a way to better quantify why some model are why some attacks they are more subtle and more tricky than others. And we can see this all the way even with other attacks. For example, if we look at auto attack, it's a suite of attacks. So there is auto PGD difference of logit ratio. This is the separation here of the logit is drastically, so the attack is powerful, and yet the energy is almost overlapping in the upper part. And the same for auto PGD, but in this case the attack is targeted. So you kind of induce the new label in the classifier, and then we see that by doing a targeted attack, you pay the price that like the marginal energy they are not overlapped anymore. And then the same it's the same for Carlini-Wagner targeted attack. Okay, so with this in mind, we also moved to analyze robust overfitting. So let me explain what is robust overfitting. Usually, once you train DeepNet, you may have a plot that looks like this one. So you have like the error rate or the loss in function of the time. You have the red curve that goes down, and then maybe lower the learning rate. It still goes down in the training set. Okay, and if you look at standard training in red compared to robust training in orange, the robust training it will more or less do the same. It goes down, lower the learning rate, and then it still goes down, and it's higher because the task of robustness is harder than standard training. And by the way, this plot, it's from a group by Zico Coulter, published at ICML 2020, where they studied the robust overfitting. And they show that things are different once you look at the validation part. So if you look at the validation part, the green is the standard training on the LDAO data, and like the error is fluctuating there. With robust overfit, with robust training, instead, severe overfitting occurs, right? Severe overfitting occurs, and the loss immediately goes up. So with Hussein, we actually study this in function of the EBM inside the classifier. And this is what we have found. So we have a similar plot. How do we parse this plot? You have on the left in blue the error rate in function of the epoch on a LDAO data, and this is standard adversarial training. And you see that like okay, the error rate goes down, and then it fluctuates but still goes down, and then in the last phase you have some sort of overfitting occurring. And this is kind of normal with SAT. So at the same time, during the same training process, we register what we call this energy divergence, so delta E. So what is delta E? Is the difference between the marginal energy of the natural data and the energy of the attack, right? The marginal energy of the attack up here. And so something important to say, while this blue curve is computed on the held out data, the green curve is computed on the training set, right? So that's a interesting remark to do. So I repeat, the blue one, it's on held out data. You want to see how the model generalized, but the green one, we computed in the training set. Okay, so we are actually looking at the dynamic on the training set. And what we have seen, this is on CIFAR 10, but we saw that it's it's the same for other more challenging data set. We see that there are, in general, 3 phases. So the first phase, the energy divergence goes down, and so it does the error rate, actually pretty smoothly. And then there is a second phase where the energy, it's almost energy divergence, it's almost constant, right? It's almost constant. And then you see that the error rate is starting to go down on average, but it's fluctuating. And then the most interesting phase is the third one. So here, what do we have? Here we have the energy divergence that drastically drops down, and this is when overfitting is occurring, okay? This is where actually overfitting is occurring. So potentially, if we are measuring the green on the training set, we have a way to detect overfitting without the need of validation data. So then we move to the state of the art that it was published in 2019 for training robust model that is still used nowadays, which is called trades. This is a paper by many authors and also Michael Jordan. It was a co-author. So what do we have with trades? With trades, we have that this is the plot. Okay, so how things are changing with trades, and now we'll explain what trades does. More or less, the trend for the error rate it's similar, okay. But in the third phase, we see that trades, it's overfitting way less, right? It's overfitting way less. And if we look at what happens at this delta energy, you see that more or less you still see the same inflection point at the same time in the training, but now the divergence is much more smooth compared than before, right? And especially in the third phase, it's not going down as it was going before for SAT. So I will play the animation once again. This is SAT, and this is what you get with trades. So let's look at what the trades does in the optimization. So unlike a SAT, where you have a brutal min-max optimization, trades, it's doing this. It's lowering the cross-entropy loss on the natural data, and at the same time, it's generating new data, adversarial attacks, but then it does so without using the actual label of the sample. So it's unsupervised, let's say. It's just looking at what is the current prediction of the model and doing an attack in order to make the model not to predict what he intentionally did before, okay? So it's an attack that in some sense it's unsupervised, and it's using KL divergence. So now you have this new point. So you are lowering 2 losses, one cross entropy on the natural data, and then the one on the attack computed with KL divergence. And in the paper, the author said that this is kind of smoothing out the decision boundaries. So what we did with my student, we actually rewrote the KL divergence in terms of energy-based model, and something interesting pop-ups here on the right. So basically, trades implicitly, it's considering in attack generation, and also in the training, it's considering this energy divergence. So I repeat that while if you do PGD with SAT, PGD, it will push down the energy no matter what. In trades, you do this attack, but you always take as reference the energy of the natural data. You are always considering the energy as a natural data as a sort of reference that you have. So and by the way, this is the same that we were tracking in the previous experiment. Okay, we can actually see this in the same plot that I showed you before. Okay, so what are we looking at? You already know how to parse this plot. Now we have the sample-wise per sample energy dynamics during adversarial training, and this is still on CIFAR 10. There is a little bit more of complexity. Before we had single points. Now instead we have arrows. So we have an arrow cloud. And how is the arrow built? On the back on the tail, we have X, the natural data, and on the tip, we have X star, which is the adversarial data. So what is the arrow? It's a sort of warping effect that the adversarial attack do to the energy. It's a warping effect that the adversarial attack do to the energy. And we can see the difference in the dynamic of SAT on the left and on trades on the right. So what do we see? We see that SAT, more or less, it goes more, the arrow cloud, no, point cloud goes more on the left, and also the arrows are more stretched, right, than trades. And also, if you see here in the diagonal, there are a lot of points, maybe the yellow one, that they are already close to loss 0. But then once you do an attack there, you are still warping heavily along the energy landscape, right? In the diagonal, the yellow one, you are still warping heavily the energy landscape. Now, if you look at trades here, first of all, the arrows, they are much more in the upper part. And like the intensity of the arrows on the diagonal, it's much less. So actually, when we found out this, Hussein online found a paper, I think it was published at Theorips, that correctly identify that the culprit of overfitting in adversarial training are points with very, very, very low loss. So they removed them from the training and they said it's improving. So here I think we go one step beyond and we show why the points with low loss, they are actually the culprit of overfitting. So we also did 2 other analyses. One was to extend this from SAT, which is kind of old method, until recent days. So what we did was to download all the models that you can find in Robustbench. So Robustbench is a state-of-the-art benchmark platform to test the robustness of model. And what we record here, if you see it, it's this delta energy in function of improving performance for robustness. So here up above, you have the robust accuracy. And you should look at this dark green energy divergence. So what we have found? We have found that the more the robustness is increasing, the more this energy divergence it's approaching 0 and the variance is reduced. So for example, trades does that compared to PGD where the green part is super huge. And so it's pushing this to 0, and then MART, it's also doing a better job to go to 0, and then adversarial weights perturbation, we have the same, and then there are other approaches, and if you see here above, the robust accuracy, it's increasing, and finally, we arrive to the best current model, which is these better diffusion models. They have a very high robust accuracy on CFAR, and the energy divergence, it's very, very tiny and close to 0. So what this better diffusion model paper does, it just simply train with trades, and they train on data generated by diffusion models that it was tuned on CFAR. So instead of having the images of CFAR, they have just like 1 million images that they resemble CFAR. And one final last analysis. There is this paper called MART from ICLR 2020. And this paper, the analysis that they did was in trying to do a very interesting ablation study where they obtained the fact that if you remove misclassified sample from adversarial training and do this ablation study, you will see that they will induce a high impact in the test error. So the idea is that, okay, let's train, for example, without incorrect sample, and then if I'm testing held out data, if the curve goes up, then it means that, oh, they matter more than the correct data, right? So this is what they take out from MART. So what we did in our case was to do something similar, but now using the energy values to do the same experiment. So we redid what they did them, and then also we tried the following. We analyzed the correct sample, so going in some sense against MART, but from the correct sample, we removed those with high energy. And we have seen that, there is even much impact if we consider the correct high energy than the misclassified. So we believe that the story is that it's not just a matter of misclassification, but it's just a matter of low and high energy sample. Okay, so then what we did, then we, given all this analysis, we said, okay, we have to somehow in the training weight the sample differently based on the energy. So we came up with this idea of weighted energy adversarial training weight, when like we simply have a weighting function that it's in function of the energy, and we use this weight to change the importance of the cross entropy loss and the KL divergency loss. And we have two variations of this. If you compute the cross entropy loss, like in trades, this is weight natural. And if you instead compute this on the adversarial sample, it's weight adversarial. And we reported the result on CIFAR 10, testing with PGD and auto attack. And also we tried that on CIFAR 100 and on SVHN, and we get statistically significant improvement compared to SAT, trades, and another approach that is still weighting the samples in a different way. So we also tried on more challenging data set, which is tiny ImageNet, and we get a similar improvement, and we compare with even recent papers. So I think DIART is from 2023. Okay, so great. So now we can move to the last part of the talk, which is about pushing the generative capabilities of robust classifiers. So what do we mean to try to improve the generative capabilities of robust classifier? It was shown way back in 2019 by the group of Madri that you can actually, from this robust classifier, as I showed you before, we can actually sample data, and you see, in some sense, feature of the class. So then the field developed, and the same paper from ICCV 2021 that I showed you before, starting from using the same classifier of Madri, was kind of showing these images. And then this paper, I have to say that they improved the result. So this is not the best synthesis that they can do. They improved the result by taking the classifier and training to be generative. Okay, they train it to be generative. Instead, here, what I'm trying to say is that we believe that we could get much better synthesis by avoiding to retrain the classifier and just improving the inference part. So this is what we were able to get in comparison of them, and these results they are produced by using the same exact model by Madri downloaded from the web. So how we did this? Prior art, what it does, it's initializing the chain of sampling from Gaussian mixture, where they place a Gaussian on each class directly in the input space. So I guess that we can do that until the images they are kind of low dimensional, such as CIFAR. And if you sample now from this Gaussian, you get this initialization, which is informative, but it's too noisy. So instead, what we proposed was to do something similar, but now on each class, we are actually sampling from the principal component. So in some sense, we initialize the init in a low rank fashion. So we don't want to get this high frequency, and so we use PCA, which is low rank. So we retain only a few components, and then if you do the sampling like this, you basically just start from the low frequency of the image, where almost already a lot of the job is done, and you avoid to ruin the data. Okay, so then how do we add more details? So we have a chain of that is called stochastic gradient longevity dynamics, which is something that it's common in the for example, the noise in score matching, and it's momentum based. So the generation goes like this: you take this discriminative classifier, you initialize xcon 0 by sampling from the principal component. So this is the mean on the class, and then you add like a variation by sampling the principal component. So now you have xcon 0, and the data looks like this, right? The same that I showed you before. And then what do you do? Then it's all about moving in the input space, right? Following the right trajectory. So how do we fall? We fall with momentum, the negative gradient with respect to the input of the joint energy of the data and the class. So what is the idea of this? The idea of this is that you want to use this gradient as a sort of guidance to move in the input space where the class density it's more likely, right? So you want to move where the class density it's better, and we have the momentum. So at the end we are incorporating this into the kind of state equation, and we add a little bit of noise to increase the variability. So this is actually the animation of the generation. Now I think it will play once again. So you start from the low frequency, and then you add details with this process. Okay, so then once we did the analysis, what we realized, in order to avoid saturated colors, we tracked the energy that we are minimizing by like chasing this negative gradient, and the energy, it has a path that goes like this. It's important to keep this energy value within some sort of boundaries of the average energy that we compute on the training set. So we saw that this is the red bar, it's the average energy that we computed in the training set, and the shades, I think they are one standard deviation away from that. If you remain in this boundary, then the data, it will still look, that you generate, it will still look natural. If you go beyond, then the data, it will start to saturate, the images, they will start to saturate and look a little bit like cartoons. Okay, so we also did a comparison with recent models that are kind of small like us on CIFAR. These are all models that are hybrid, which means they also trained for generative modeling. And we are here at in the lower part, so we didn't train anything, just improve the inference. And we get nice feed by using a model from 2019, nice FID, and then we get a good inception score. If we use a newer robust model, we get much better FID and state-of-the-art inception score. So to repeat, we are comparing the FID, even though it's not state-of-the-art. Here we are using a model that it's simply trained with adversarial training with trades, and the feed is still lower than model there above that are trained to be generative, such as GEM and JET and GEM++. Okay, so now let's look at the images the way they look like. I think in my display they are a little bit less saturated than this. Okay, so we also compare the generative capabilities of training with SAT and training with trades. So you remember this plot, right, where SAT, it was warping much more the energy landscape. So we can actually see this plot in the generated images. So there we go. Here on the left we have SAT, and then on the right we have trades. And you can clearly see while trades, it's more mitigating the fact of warping the energy landscape. It's producing images that they look much more natural. Instead, SAT, it's producing these over saturated images, and even the optimization dynamic is different. SGL for SAT, it's converging in 20 steps, and trades in 150 steps. So it's much lower in convergence. Okay, so here we are adding in the final part of the talk. So in this part, we want to perform image synthesis and editing by inverting a quasi-robust classifier, and we want to guide the editing through a mask. So this is actual work done with Mozde that was before at USC, Masood at UCLA, and Iacopo at USC. So what we did, I think now you have all the tools to understand. So the method goes like this: you have X, it's an image, and someone, it has to tell you and give you a binary mask of the object that you would like to modify, the binary mask of the object that you would like to modify. And so you want to edit this X, okay? So how do we edit it? We edit by producing X prime, and you want this X prime to still share the similar feature of the class of X. So what does it mean, this path? It means that you encode X with a quasi-robust classifier, and then you decode it by inverting it. So now you have X prime that it doesn't look nice. So how do we make it look nice? We work at the patch level. So we have a patch gun that makes that the patches of X prime, they resemble X. And then how do we change the shape? Now, maybe an artist will tell us, oh, I want to change the shape mask Y prime, and somehow we enforce the new mask into X prime. So if you see, X prime, it's receiving 3 arrows and input. It's like same class, the patches have to be similar, and please change the mask. And this is reflected in the architecture. So we have X, which is the reference image, and then as input we have the segmented object. And by the way, here there is anything trained except X prime. So it's kind of a sort of lazy learning. So the quasi-robust model is fixed, downloaded from the web. And then the green encoder decoder, it's, let's say, very, very quickly pre-trained to map from X to Y. And then once we are optimizing X prime, they are all locked. So the yellow architecture and the green one, they are all locked. Okay, so we optimize the input. So we are optimizing the input. So how does it go? You receive 3 gradient on X prime. You receive the gradient from the quasi-robust model in order to get class features. You're receiving the gradient of the discriminator because you want patches to be similar to X. And also here it's interesting, on the green one, you do this. You learn before the mapping from X to Y. Then once you're optimizing X prime, what do? You change the label into Y prime, and you receive the gradient on X prime so that X prime, it will match Y prime. And finally, maybe you get, after the optimizing X prime, you get your change. So with this, we could do non-rigid scene deformation. You have mountains, you try to segment the profile, and then you say, okay, I want to use them like that, and then you have to run an optimization, so it's a little bit slower, and then you get the new image. And then we can also do copy move things. So in case you have repetitive patterns, you maybe have flowers, you say, okay, I want to remove them and add some others. So here we just put an oval where you want the flowers, and then the gun, it's helping us a lot in order to make this look nice. And we also did qualitative comparison with other approaches. For example, imaging, which is by Adobe, and then DeepSim, and then Magic, which is ours. And we, for example, can try to open the wings to this bird, and make the squirrel large. And we can try to change the shape of the fish. And I am Italian, I like spaghetti, but I like them to be round. So we try to make them round, and then we also tried on scenes. So overall, the DeepSim, it's working very well. I think it's overall better than us, but it's once you train it, it's warping the input images as a data augmentation step. So you see that somehow this nonlinear warping, it's reflected in the output. Okay, so I am almost done with my talk. So I would like to summarize what hopefully we have learned today. The first take-home message is that there is not a clear distinction between discriminative and generative models. And secondly, adversarial training, we believe that it can be better explained using this lens of generative modeling. And finally, hopefully, we have a better way to combat robust overfitting, and we can understand it and detect it. And finally, I showed you a few applications that you can do with robust classifiers. So I believe that there is a strong connection between robustness and generative AI. So we are also now working on other things. So for example, Maria Rosaria is working on bridging adversarial training with diffusion models, and she's also working on proactive image defense. And Adrian is working on LLMs as energy-based model and also on model stitching. And Antonio is working on inverse problems and constructive solid geometry. And finally, Hussein, which is a part of this work, he works on robustness and models that are hybrid, discriminative, generative. With that, I am kind to end, and I am organizing a workshop at ICCV 2024 on unlearning and model editing with other colleagues of mine. So if you are working on this concept of a foundation model, you want to remove some concept or you want to edit the model, you are welcome to. We are accepting papers at this workshop. Unlearning and model editing, you and me at ICCV 2024. That, by the way, it will be in Milan, so I will be there. Okay, cool. So with that, I end my talk, and I thank you for your attention. Thank you so much.
I have a simple question, which is, what does it mean for classifier to be robust? I know it's probably a technical term that I'm.
For classifier to be robust means that you have to somehow define a threat model. You define at least what we did before with Covenant and so on. Now with LLM, things are changing, but with Covenant, you say, I am defining the threat model. So the attacker at most can move in the input space using this metric and so on. So, you define a sort of deformation that it's allowed in the input space. Now, this is your threat model. And then how do you make the model robust so that if an attacker tries to produce input in that boundary, the classifier, it has to be safe. Classifier, it has to be kind of, safe. Now, all these regional adversarial attacks, it's a little bit, changing with LLMs because the input space of LLM is discrete, it's text. So there you can do you replace words and so on, or if you go with the gradient at most, you can arrive on the word embedding, but then it's changing a little bit the field. But the research in adversarials, they are still now applying these ideas on LLMs, and I believe also I saw a talk at CVPR, and OpenAI also now it has a requirement that in order to test the LLM, they want them to be robust to this kind of perturbation. They want them to be robust. Yeah. Yeah. Well,
you were just talking about the LLMs, right?
Yeah.
So I would assume a multimodal LLM is much more easier to attack because it has a continuous space from an image patcher.
Yes. Okay. So. So if you bring in the text, I have seen the different things. So for example, I have seen that they place the attack. For example, that there is an apple and they place a badge, a sticker on the apple with written iPod, and then now Clip or another foundation model will tell you, oh, it's an iPod, it's not an apple anymore. So it's a different kind of attack. More in the physical domain rather than on the pixel domain. And yes, if you have two modalities like visual and large language model, then also you can still do similar attacks. You can.
So do you think the effectiveness of let's say Carlini-Wagner or a PGD would be a lot reduced because there's text in the multi-modal? Because now your attack space is lower, right? You have few patches to attack.
Yeah, the attack space for the text, I would say it's more kind of combinatorial than continuous optimization. So it's more kind of combinatorial because it's discrete. Yes, but of course, yeah, if you have images, you can apply all these techniques straight to them. So if you have images, then you can apply, yeah.
Let me see if anyone online has a question.
Yeah.
Hey, this is Mohammed. Can you hear me?
Yeah.
Yeah. Just a question about when you showed the difference between the behavior of different attacks. There was Carlini-Wagner has a different behavior than PGD. Do you think this is because of the algorithm or because of the kind of norm they use? Because one of them used two norm, one of them used L infinity. I mean, are you comparing the same norm or just algorithms?
Yeah, it's the same norm. Nice, Mohammed, to hear you. So it's the same. Let me go quickly to that plot. I believe it's the optimization. I believe that it's the reason for this to be different. It's not in the norm, but it's in the optimization of the attack. And actually, that's why Carlini-Wagner is a much stronger attack than PGD in some sense, because you still want to you still want to flip, you still want to flip the label, but at the same time, in terms of, like from the point of view of the model, if you compare this marginal energy, which you can think it as a sort of probability that the model is estimating of being inlier or outlier, they are much more overlapped, right? So that's probably why the attack it's tougher, because I think also Cardini is looking for the like minimum perturbation in the input space, right? So I think it's looking the minimum perturbation in the input space, and I think yeah, go ahead.
No, I'm just acknowledging that I'm hearing you.
Yeah, cool. No, it's a very interesting question. Yeah.
If you have a minute for another question, I have another question actually.
Yes.
So when you compare, so if you look at the dot plot, so now you're comparing these the energy of adversarial examples to the energy of assume testing real examples, right? So this example is not used during training. So I think the comparison may not be fair, because for one of them you're optimizing the loss. I mean, you're finding the example that optimizes the loss in a certain way, but in the other you just take the image as it is. So what do you think would happen if I take the clean images and try to change or perturb the image to actually enhance the loss on this specific image? So what do you think will happen there? I'm not sure if I'm clear.
So what you want to do? You say, oh, the clean point that they are as it is, and the red point you are actually optimizing them, so it's
yes, it's
right?
not like a fair comparison. Maybe we can also take the clean points and optimize them too, like enhance the logic of that example based on the class and then maybe they will move in the same direction. Then you cannot distinguish between them, or you may be able to distinguish between them. I don't know.
I think once you create an attack, the x-con 0, the init point for the attack, it's the natural data itself. So I think in the red it's already doing what you mean. You start from the natural data, and then you move the natural data in order to make this happen.
Yeah, you're moving it to maximize a wrong logic, but if you move it to maximize the correct logic, I think you will get, that's what I mean.
I see. So I see. Okay. So you want to do some sort of friendly. They are not attack anymore, right? You want to do some sort of friendly. Okay. Let me think what it may happen. So you take the clean data instead of doing an attack. Maybe the model is not getting it right. You on the new point, instead of doing an attack, you want to lower the loss.
Mm-hmm.
Okay, so if you lower the loss, probably what you would get, it will be the opposite of PGD. So I think I can predict this experiment. So in this case, E of X, it will move on the right,
mm-hmm.
and the logit will move on the left.
Okay.
So I am predicting that this will happen, because if you see here the equation of the cross entropy loss, if you see the equation of the cross entropy loss, where it is, let's see. Now it will come. There we go. So once you maximize this, you are pushing this on the left, right? Because there is a minus. And you are pushing this on the right, right?
Yeah.
So now, if you minimize it, you get the opposite of what we did with PGD. So probably you will get that the marginal energy which goes on the right, and then the logit it will get more right in some sense, right? Yeah.
Okay, I will follow up in our one-on-one meeting.
Yeah.
Thank you.
Yeah, thank you.
Any last questions? Thank you.
Okay.